So let's talk about general theory of relativity.
Ah, a classic. The general theory of relativity is Einstein's masterpiece from 1915. It fundamentally reshaped how we think about gravity, not as a force pulling masses together, but as the curvature of spacetime. Massive objects like stars or planets bend spacetime around them, and other objects follow these curves. It explains phenomena like gravitational time dilation and the bending of light, things Newton's gravity couldn't. It's elegant, yet it'll challenge your intuition every step.
Okay, can you give example how actually our modern GPS work and how the time zone also work because there are multiple time zones, but we can see that.
Sure. So GPS relies on a network of satellites orbiting Earth, each with super precise atomic clocks. General relativity is key here because time in orbit ticks a little faster than on Earth due to weaker gravity. Without correcting for this time difference, GPS would be wildly inaccurate. The satellites broadcast time signals, and your GPS device compares them to determine your exact position. As for time zones, they're just human conventions dividing the world into regions with standard times. When you see different time zones on your device, it's simply adjusting local time based on your location. GPS helps identify where you are, and then the device knows which time zones offset to show you.
So basically, that GPS relies on a network of satellite orbiting Earth. Can you explain that part?
Absolutely. GPS satellites are orbiting Earth at about 20,000 kilometers up. Each one continuously sends out signals containing both the exact time from their atomic clocks and their position. Your GPS receiver picks up signals from at least four satellites. By comparing how long each signal took to reach you, it calculates how far you are from each satellite. With these distances and satellite positions, it triangulates your exact location on Earth's surface. Without accounting for relativistic time differences, those distance calculations would drift off quickly, but relativity keeps them accurate.
Can you explain in more detail exact location on Earth's surface?
Of course, to pinpoint your exact location, the GPS receiver measures how long each satellite signal takes to reach you. Since the signals travel at the speed of light, the time delay is turned into a distance. By knowing your distance from multiple satellites, the receiver solves a geometric puzzle, basically where spheres around each satellite intersect. With signals from at least four satellites, the receiver can determine not just your latitude and longitude, but also your altitude. On top of that, it adjusts for any clock error in the receiver, ensuring that your position is accurate down to a few meters.
Can you explain that geometric puzzle part?
Imagine each satellite as the center of a huge sphere. The radius of each sphere is how far you are from that satellite based on how long the signal took. One satellite sphere alone doesn't tell you where you are, you could be anywhere on that sphere. With two satellites, you get a circle where those spheres intersect. Add a third satellite and you narrow it down to two possible points. Usually one of these is nonsense, like off in space. The fourth satellite helps confirm your exact point, plus correct any time offset in your receiver. In the end, where those spheres intersect is exactly where you are on Earth.
Can you again give broader picture of that satellite and that calculation part that you are mentioning about?
So think of each GPS satellite as sending out a message saying, I'm here and it's this exact time. Your receiver gets that signal and knows how long it traveled, so it calculates how far you are from that satellite, like drawing a big invisible sphere around it. When you do this with multiple satellites, these spheres overlap. The place where they all meet is your position on Earth. The calculations involve solving a set of equations based on those distances and satellite positions. By doing this rapidly and continuously, your GPS gives you your coordinates in real time.
What do you mean by that satellite position?
Exactly. Each satellite knows precisely where it is in orbit at any moment. This is calculated using orbital mechanics. The satellite broadcasts not only the time, but also its own coordinates in space. Your receiver needs these positions, where each satellite was when it sent the signal, so it can accurately solve the geometry. Without knowing where the satellites are, the distance alone wouldn't be enough. So your location is a combination of how far you are from each satellite and where those satellites were in space at that exact time.
Can you explain that when satellite is orbiting around it, what do you mean by that, and how GPS is related with that fact?
When I say a satellite is orbiting, I mean it's continually falling around the Earth due to gravity, but moving fast enough to keep missing it, so it travels in a stable path around the planet. GPS satellites follow specific, predictable orbits, so we always know where they'll be. GPS relies on these orbits because precise satellite positions are crucial. The system constantly updates where each satellite's supposed to be. When your receiver picks up signals, it uses not only the timing, but also each satellite's orbital data. That's how it can figure out exactly where you are on Earth.
But for getting the GPS data, what do we mean by that point? And do we need a satellite orbiting around the Earth to get the relevant information?
When we talk about GPS data, we mean the information your device receives from the satellites, things like the exact time, the satellite's position, and the signal travel time. Your device needs at least 4 satellites' data to solve for your position and correct timing. So yes, without satellites orbiting Earth and transmitting, you wouldn't get GPS data. These satellites are essential. They provide the signals that let you know exactly where you are and what time it is.
So what you are basically suggesting about that satellite positions?
What I'm really highlighting is that the satellite's positions are known at every moment. They follow predictable orbits, and this information is constantly updated. When the satellite sends a signal, it includes its exact coordinates at that time. Your GPS device uses these known positions, along with how long the signals took to get to you, to solve the geometric puzzle and figure out your location. In short, knowing where the satellites are in orbit is a key part of how GPS determines your position on Earth.
Can you give example from general relativity that how that one concept and application based things are used directly here in GPS case?
Sure, general relativity tells us that gravity warps time. Since GPS satellites orbit high above Earth, they experience weaker gravity than we do on the ground. According to general relativity, clocks in weaker gravity run faster. The atomic clocks on the satellites tick slightly faster than clocks on Earth. If this, GPS location would drift off by kilometers each day. So GPS applies relativity corrections, adjusting the satellite clocks so they align with Earth-based time. In other words, we use Einstein's theory daily to ensure GPS accuracy. Without it, GPS simply wouldn't work properly.
Okay, can you make conclusion what we are discussing till now?
In a nutshell, we've connected the theory of general relativity to how GPS works in practice. Because gravity affects the flow of time, clocks on satellites orbiting high above Earth run faster than clocks on the ground. GPS accounts for this by applying relativity corrections to its satellite timing. By knowing exactly where satellites are and precisely when signals arrive, your GPS receiver calculates your position. In short, Einstein's theory ensures that GPS can accurately guide us, whether it's to the next city or just around the block.
Okay, thank you.